hopefully you can see my screen now. And also, feel free to write any comments. And we will have a dedicated space for discussion after the brief presentation that I'm going to do about the survey overview we did and the literature overview we did about submicron and ultrafine particles. We are very strict with time, so we only have 60 minutes, and let's count them. So, particulate matter. Currently, we can see and we can regulate only this small fraction of PM, which is PM 2.5, in some cases PM10 as well. But underneath the surface, there are more particles, right? Submicron and ultrafine particles. And today we would like to explore a little bit more and have a discussion all together to see what we can recommend potentially through AQS to the research community and policy around those two parameters. A few days ago or weeks, I shared on social media this image where we compare the PM 2.5 against ultrafines, and we were discussing about the 1 to 2.4 million ratio, and the fact that one particle of PM 2.5 in aerodynamic diameter, it's going to give us 10 micrograms per cubic meter in mass concentration, and the same number is going to be giving us by 2.4 million ultrafine particles of 20 nanometers, according to this specific study. Later on, I found more information from some other researchers where they had different sources of PM pollution from Sahara dust, biomass burning, secondary aerosols, urban background, and traffic. And although all of them, they had a PM 2.5 of 12 micrograms per cubic meter, they have So this is something else that we have to consider as mass becomes more irrelevant when it comes to the health outcomes, as we are going to discuss later on as well. So let's begin with submicron particles. From the survey, 47% of the respondents say that submicron particle monitoring is important based on empirical evidence, and 47% again, they say that it is still unclear and requires further study. So in total, 94% of the people agree that we need to investigate more submicron particles and start measuring them indoors. Health risks versus PM 2.5, there is a strong consensus, 95%, that measuring submicron particles is a superior indicator of health impact. Now, technological speaking, 42% of the experts stated that technology is not yet sufficient cost efficient in order to have a wide adoption. On a little bit research that I did, I found that particle counters range from 150 to 1,500 euros for the sensor, the electronic component, not the final product, but they comply with the ISO 21514 that has specific requirements for particle counters for different sizes from 0.3, 0.5, etc., in order to have accurate results and comparable results among different instruments. Finally, among the survey, most experts agreed that we have to use some kind of a different metric, like particles per cubic centimeter, instead of mass, although some of you, like if I remember one person suggested like nanograms per cubic meter to maintain compatibility with existing regulatory standards. However, I think it's challenging to continue using mass. Now, the literature share that I had the opportunity to review had the following findings. Some microparticles penetrate deeper than PM 2.5. PM1, which is another term to use for some microparticles, has been reported to have a stronger association than PM 2.5 with lung cancer, cardiovascular disease, and childhood pneumonia. And then findings highlight that PM1 is primarily a byproduct of human activity, especially fossil fuel combustion, rather than natural processes, comparing to PM 2.5 as well. The main components of particles of PM1 is dominant organic matter, sulfates, nitrates, black carbon, and ammonium. Again, it's an anthropogenic nature, make it more targetable for regulatory than PM2.5 for regulation. So some researchers out there suggested that it is easier to set standards around that number and see the results pay out as those particles are generated by humans, right? And finally, some trace metals were found in some PM2.1 particles, specifically from vehicle emissions and brakes, right? Something else that I found very interesting to discuss is that in some literature, when they discuss about PM1, they also include ultrafine particles, right? Because when you say PM1, you are referring to any particle less than 1 micron, which includes nanoparticles. In the indoor space, unoccupied indoor environments often act as sinks, which means that basically after a while, particles start to settle, and with concentrations typically being 50% lower than outdoors. Now, there is a problem when it comes to submicron particles coming indoors, as they have a way to penetrate and infiltrate inside buildings, and they found like 75% of them from the outdoor come to the indoor space. And also we have to keep in mind about the MPPS, which is the most penetrating particle sizes, which is around 0.3 micron. And this is the specific size that we would like to explore inside AQS. Volatilization is another characteristic we had the chance to see when outdoor air enters warmer indoor environments. Some ammonium nitrate particles often volatilize, which means turn back into the gas, and rather reducing the indoor particle mass. And finally, researchers regarding some microparticles in indoor environments indicate that while buildings act as a protective shield against outdoor pollution, the indoor air goes significant chemical changes once ambient air is infiltrated. And also, and we will see that later on ultrafines, indoors, we have the generation of secondary particles in the size of nanoparticles in the indoor spaces because of the chemistry and temperature conditions. Now, when it comes to what's the best metric for submicron particles, again, several papers argue that mass concentration is not the right tool for us. So they suggest particles per cubic centimeter. Some others are suggesting lung deposited surface area. And some others, they talk about the oxidative potential, which is a toxicology relevant metric that measures the capacity of the particle matter, including its chemical and biological components, which now creates an obstacle because not all of the instruments out there can measure the composition of those particles, right? It becomes very expensive very fast. And for the lung deposit surface area, we need the particle number plus the size in order to calculate that specific metric, which is easier. Not as easy, though, than counting the size of the particle, but it's easier than the oxidative potential. Now, I tried to find any regulation around particles, specifically for 0.3 and 0.5. And the only thing that I was able to find was the ISO specification 14644-1, which is related to the clean room standards and a US equivalent that basically say they have different classes of ISO. And they say that particles shouldn't surpass this specific number inside an indoor environment. I converted those numbers in particle per cubic centimeter as they are easier to digest, I think. And then I extrapolated for 0.3 as they haven't had any number around them for ISO 8 and 9. And I tried to compare them against some unpublished measurements that I did in an office environment and background seaside environment as well. So for 0.3 and 0.5, we had 8.4 particles per cubic centimeter and 1.1 in indoors. which is quite low, right, in comparison to the ISO specification, even for the ISO 8. And then for the outside environment, as a background reference, let's say, for 0.3, we have 45.8 particles per cubic centimeter, and 0.5, we have 5.4 particles per cubic centimeter. Now, something that we've discussed in the previous meeting in the morning is the particle size range and what instruments we are using, as in most cases, not all manufacturers out there align their instruments with how we communicate our quality or measurements. For that specific ISO clean room ISO specification, they use particle counters that they comply with the previous ISO standard that I've mentioned for particle counters. And for that specific reason, they use particle range from 0.3 to 0.49. And for 0.5, they measure a range of particles from 0.5 to 0.99 microns. So we have grouped them at PN 0.3 and PN 0.5 particle number, right? For some researchers, this is confusing, apparently. And I would like to hear your comments later on from the people in this call as well. Again, we have 11 people, I see. Now, ultrafine particles, during the survey, again, most of the people said that it's important to measure it. However, and it has more impact on human health. However, it is more difficult because of the price of those instruments, that they can range 5,000 to 15 or even more now, depending what we would like to measure. And it's a significant barrier. Again, the majority agree that we can use particles per cubic centimeter, but some other experts that we have, professors, they suggested the lung deposit surface area is a more adequate metric. The literature says the same thing as submicron particles. They go a bit deeper by saying that chronic exposure to ultrafines includes several lung inflammatory responses, massive macrophage infiltration, basically the mechanisms that we have inside our body to find particulates or foreign objects and remove them. They cannot even do anything about those nanoparticles. So they end up be absorbed by the tissue and create some other problems by even exploding some of the tissues, which, by the way, there is a video out there recorded by some scientists where we can see the human cell explode because it has absorbed some particulates. Higher sensitivity translocation, which basically means that those particles can cross the alveolar capillary barrier and travel to major organs and then create problems there, including the brain, as we can see, heart and other human organs, and higher cancer risk as well. When it comes now to the metric, what kind of metric we should use for ultrafines, according to the literature out there, no, sorry, this is not the correct slide. This is the one for the metric. Let's go a little bit back and talk about what we found about indoor domestic activities and ultrafines. They say that in many cases, those levels can be, the ultrafine levels indoors can be way higher. The reason is grilling food using hair dryers, and actually hair dryers was one of the highest mean in order to create ultrafines in a domestic environment. And also like frying, cooking, burning candles instances, and using laser printers can also create ultrafines. In the hospital environment, smaller ultrafines exhibit lower air exchange due to stronger Brown emulsion, which makes them more difficult to remove than larger particles. So we also have to keep in mind that. Now about the metrics, yes, most of the scientists out there say that mass is not the right tool. Particle number concentration should be used. Again, there was a debate in the morning about using like something like lung deposit surface area. But in many cases, they say that instead of proposing a single safety threshold, the research discussed why current standards are insufficient and suggest technical improvements for further regulation. As regulating PM2.5 mass may not significantly reduce ultrafine particle levels, right? They're not well correlated, and I have some example that I have of my own. And then some other researchers suggested using something called reference value, which basically is taking a recommended background concentration measurement and then taking an actual measurement in order to determine if there is any change in the environment or not. According to the research again, to the literature, rural background, approximately levels are approximately to 2,600 particles per cubic centimeter. The global urban mean is around 10,000 particles per cubic centimeter. The roadside hotspots can reach concentration of 48,000 particles per cubic centimeters. And indoors, some extreme events can create concentration of 2.3 million particles per cubic centimeter, which is huge. Currently, we have WHO recommendations. I'm not a fan of them, not for any other reason, but because I think they create a confusion, especially if we have 24-hour and 1-hour mean values. And here is an example from some actual measurements indoors here in my apartment, unoccupied. So a 24-hour mean gave me a 2,900 particles per cubic centimeter, which is above the low threshold. And the 24-hour mean, again, for 2,900 particles per cubic meter, it gave me a well below high risk value, right? And finally, in 1-hour mean, which was 1,500 particles per cubic centimeter, was extremely low. So now it is very challenging for me to understand if I'm in a safe range with those ultrafine particles in the domestic environment. So here are some experiments that I did with unpublished data. In that specific example, we see a very strong correlation of PM2.5 and ultrafines. But the reason here is because the indoor setting was unoccupied. Not much of concentration of PM was happening. We didn't have any source of pollution coming apart from some infiltration, I will assume. So for this reason, we have this high correlation. Outdoors, though, we have a weak correlation between PM2.5 and ultrafines. And I think the reason is now the complexity and the real sources of air pollution that have contributed to this result, right? A summary of what we see so far is that when it comes to the size definition for submicron particles, and when we say particle number 0.3 or 0.5, we talk about those ranges. And for ultrafines, we are talking about 100 to 10 nanometers in size. The health effects is obviously common for both. They have bigger correlation with health outcomes than PM2.5. The sources, again, are more anthropogenic rather than natural sources. When it comes to submicron particle, experts claim that it's time to start investigating more by 94%, where for ultrafines we have 53% of them considering monitoring ultrafine. And I think the reason for that is the cost differences between instruments that are able to measure those different sizes of particulate matter. As I've mentioned earlier, 150 to 1,500 euros for the sensor for some microparticles, but we go from 3,000 to 50,000 euros or more for the ultrafines. And then again, the preferred metric, I think for both is particle per cubic centimeter, but for the ultrafines is also the lung deposit surface area. So now time for discussion for some microparticles. This is what we find. Do you agree? Do you have any comments? Feel free to raise your hand. ask questions, express your opinion. We're here to hear everyone. And don't be shy. Aaron, please.
So I think the first question I have is, what context in this do you consider for the balance of like health effects versus the metrology to do it, right? Because I feel like what always happens in these scenarios, especially with ultrafine particles, is that there isn't sufficient outdoor data yet to derive health impacts. So we like have this like chicken and egg, right? So how do we create requirements for UFPs based on ultrafine outdoor data that's tied to health, to health data associated with exposure to that, which then ties to regulation. We don't really have that yet. So to me, I think kind of some of the ways that you're discussing is like, well, I want ultrafine, but they're too expensive, so we're not going to do it. But one way to do it is to say, let's create a roadmap, right? We know that there's that ultrafine particle monitoring is getting cheaper, right? If you were to go back 10 years ago, there was like no diffusion chargers, right? There's no lower cost CPCs. And today you can buy 2 CPCs that are under $5,000. Our version, but Suzanne Herring has hers, the water-based CPC. There's lots of diffusion chargers that we're seeing coming online. So that price can go down over time. And so I think creating a roadmap to say, where are we today and what metrology do we want to use today? And how does that come with a standard today? And what's the roadmap for the future, right? Which we don't have a perfect vision. What is it? LDSA, long deposited surface area? Is it long deposited surface area times the expected oxidative potential? Because it's a combination. Is it, that you can create all kinds of different metrics that don't exist yet. But I think you should include them. I think you'll get caught in the chicken and egg problem too. So the answer is to say, what technology do we have today and what can we answer today? And how would that help people? What technology do we need in the future? How would we structure a standard in the future? And how would that help people in the future? And I think separating those might give more clarity to the problem.
Exactly. You are absolutely right. This is the reason we have this call, in order to figure out that specific obstacle, if you like. And from my perspective, even particle counts per cubic centimeter is enough at the moment to have a little bit better understanding. And in the future, if those devices can measure also the size, then easily can be converted in LDSA, right? Is not the problem. And with LDSA, then we have another problem. Are we talking about which area of deposit in the alveolar or upper lung, right? And we have different metrics there as well, which now it creates more confusion. Why? Because we need more data again, and more research, and more.
And you have to know why. It's also good to think about why LDSA was invented and who are the proponents for it, because there's different ways to think about the problem. And different metrology that sometimes gives you LDSA, which is, it's fine. I don't really care either way, but like some of that is like, it was an easy metric to generate. And so we created a new metric because it matched the existing data set of metrology. But is that what we want to use going forward? I think when as you kind of look at this, and I don't want to dominate too much, so cut me off at any moment. But I think as you think about particle number count and you look at urban settings and indoor settings, the question kind of asks is, what's the correlation between particle number count and PM2.5? And kind of what you saw in your graph of your kind of, I don't know exactly what you used to measure it. Probably a low cost PM sensor would be my guess. Was that your reference? Was a low
PM
cost?
2.5, yes, which I had collocated, and I was a little bit certain about the measurement.
And you got to understand the limitations of low cost PM2.5 sensors. I think people are starting to realize that they are optical particle counters. They're shitty or not very good optical particle counters that masquerade as mass measurements, which is okay. Again, I think as long as everyone's transparent, like they're not great in terms of mass, that's okay. We just have to acknowledge that. But they are good number counters. Number count. They're bad at sizing, but they are good at count. And so they're actually, and sometimes when you recontextualize it, you start to say, well, actually, what is the strength of low cost sensors? It's number count, actually. And then what is the correlation of PM2.5 in an indoor space to number count? And I think in low cost sensors, they are very tightly correlated. I think in most of the work that I've done, looking at PM2.5 and ultra count, looking at PM2.5 from low cost sensors and number count, they're like 90% correlated. I have a bunch of data for indoor. Outdoor, different ballgame, because resuspension, dust suspension, they don't even do PM10. Don't even use them for that. They give you a number, but they don't mean anything. So I think combining the technologies and then their strengths may help you come up with a better way to think about what the metric should be, because you're kind of already implicitly saying, I want a standard that has metrology available today that I can use to create a standard. And so then you should say, I want to use these methods and they're good at this. And that's why the standard should be that, and not use PM, particular mass at one, because are they good at that? Or is that the why, if that's the thing that they're not good at measuring, then why should we use that as the standard? Because then someone else that measures PM in a different way, a TOM or oscillating.
Let me jump in. My raising hand is not working.
No, you're all good.
Can you hear me?
Yeah.
I have fundamental problems with this. Optical particle counters do not measure PM. Let's stop calling that as PM. It's completely bogus, false, and incorrect. PM is a statutory measure. It's strictly based on aerodynamic particle size. I should know, maybe the only one left, because I was involved in collecting data and helping the EPA develop the PM standards in the 70s and 80s. Little history. We went through some of the questions you're raising about PM1. We went through it in the 70s and 80s. The only reason we don't have a PM1, partly I think you addressed it in a different context, they could not come up with a sensor for aerodynamic size of PM1 that is economically viable for people to install all over the world. And the conventional wisdom at that time was PM1, any particle aerodynamic size of 1 micron is already included in 2.5 for health effects. And the rationale for the mass came from the medical community, inhalation medical community, where almost all health effect, go back to medicinal chemistry, is based on mass, not on volume. If you take a prescribed drug, how much you take is based on the mean response volume for that drug for the median weight of the population. They give you some, I don't remember the statistics. That's why the mass comes through. That's why they set the mass. If I remember right, don't quote me from memory, they went for the threshold limiting value of maybe the top 5 hazardous particle aerosols in the atmosphere, looked at the TLV, and I believe they set it at half that value as the outdoor ambient air quality standard. So these are strict. Why aerodynamic size? Because it is not arguable anymore that what goes into your lung through your nose and the trachobronchial system is based on the aerodynamic properties of the particle, not the optical properties of the particle or the electrical properties of the particle. So we can use particle counters. I'm not against it because it's convenient, cheap, available everywhere, but don't call it PM. If you really want to call it, let's call it DP 2.5.
Right, like we don't call it, like at GoHead, we don't call them.
All your slides
the researchers
keep saying
sometimes confuse
all your
it.
slides keep saying PM, so don't say you don't call it.
The
second part, hang on, let me finish.
Okay.
The second part, more recently, I believe the late 1990s, early 2000s, there's a lot of work done by NIOSH, perhaps also the European equivalent, considering the effects of nanoparticles. There is some evidence, some medical data, that the effect of nanoparticles on the human health is more closely related to surface area, not the mass. But they could not come up with a simple, inexpensive, repeatable measurement technique to determine surface area of particles. Because not all particles are nice and spherical. So there is no direct measurement device that gives you surface area. And so curious, one correction in your slide, unrelated to this, HEPA filters MPPS is not 0.3 micron, never was, never will be.
It is around that size, according to the research that I have done.
No, I write the standards for it. I'm the chair of these committees. It is 0.3 micron in the mass median diameter. The count median diameter of the same one will be closer to 0.18 to 0.17. So keep that in mind. It's never was at 0.3.
All right. And to answer your previous comment, the literature is calling it PM1, but as you can see here in the last slide, I have called it particle number 0.3 for that specific reason, because we see that there is a confusion out there when they use the term PM, as people have associated with mass, and we do not want anymore to associate particles with mass in that specific size, but rather with number.
But you referenced PM 2.5 in your other slides.
Yes, because we were measuring PM 2.5.
You're not measuring, you're using particle counters. They don't measure PM.
Well, they estimate, if you like, or they calculate.
They don't estimate at all. There is no equivalence. What is equivalent in your apartment will be very different than in my lab. One is an optical diameter. It gives you, I'm not saying it's good or bad, it's convenient. So I think we should stop calling PM. Let's not be ashamed of using particle counters. It's a good device. It gives you good, repeatable data, inexpensive. People can use it.
Well, sure, but again, I didn't use a particle counter for that specific scenario. I used a low-cost sensor that has algorithms to calculate the mass based on the counts that they were able to measure.
It's not on PM. I'm sorry, it's not.
It is not a number. It is not a PM number, but it is an estimation.
No, I think you're missing the point. You don't label it. The data is good, but it's to call it something else. It's like saying a kilogram is close enough to be a pound. They are not. I'm sorry. The more you use it, the more I'll object.
Okay, Florian, you have raised your hand for a while.
Yeah, thanks. Well, first of all, thank you for putting this together. I think it's actually quite a good overview, and I think it exactly tells us where we are at the moment. So I just want to comment on, I mean, you mentioned this, we call it PM1, or we can argue whether we call it PN, agreed. But the point is this, whenever we talk about, I think we really distinguish between submicron UFP particles here. So I actually like the idea of that we rather define the lower limit, which would be the detector limit in that case, saying PM 0.3 would be everything that is just larger than 0.3 micron, to just distinguish this from ultrafine particles, because we don't want to create the impression that these low-cost sensors can actually also measure UFP when you say they detect everything smaller than 1 micron.
Exactly,
Maybe
like all of the low-cost sensors, they cannot measure below 300 nanometers or 0.3 microns. So that's the reason, again, we try to differentiate it and also differentiate the group of ultrafines and submicron particles, because they use different technology to measure them, right?
Right. The question is, do we need to limit the upper size? Do we really need to limit the PN 0.3 to 0.3 to 0.49 as you say here? Because I would assume that most of the particle number actually happens below 1 micron, and even if you include the particles that go up to 10 micron, it doesn't add up to your number count in that sense. So do we really want to make it that narrow in a certain sense to complicate the metric in this case?
I took those numbers out of the clean room again industry, where they use those particle counters in order to measure those specific ranges. So they have set already those products to measure those.
I know they have bins, but I think what they actually count is that they will also count anything that is larger than 0.5 or larger than 0.3. They will include all the other.
Depending the bins and how they have classified them, right? When it comes to 0.3, this is the numbers that they give, and 0.5. And then when it comes to 10, for example, microns, they take 10 and everything above that they can see, even up to 75 microns in diameter particles.
Okay, I will need to read up on this. My understanding for the clean room standard was always, if you call the 0.3, then they will count everything above 0.3 and not only that bin. But maybe I'm wrong here.
There is it's complicated, and there are two ways to measure it. You are partial right, but I will send you more information after the call if you like, because I used to work for that industry, and I know from fact how they think about it.
Good, that's good. Then I also like that. Then I have one comment about lung deposited surface area,
Mhm.
which I mean, I also have some background, I think, on where it comes from, or at least how to measure it, at least. So LDSA is actually a metric that comes out more or less by default out of diffusion charges. So it's something that is, in that sense, measurable. And it's actually, for diffusion charges, it's actually easier to measure that than the particle number count, because it's kind of the inherent signal that you get. You actually need to do less conversions for diffusion charges to get LDSA. I personally, and I mean, I produce diffusion charges myself, but I would still not vote for LDSA, in a sense that at some point, you know, people in other industries decided for PN when it comes to ultrafine particles in terms of harmonization. When you think about automotive industry, when aviation industry, you know, regulations that exist on the emission side, and all these discussions have been done before. And I think we also want to harmonize with what is already out there, and rather stick to counting than creating a new metric, unless you really want to reinvent the wheel. But then you come back to a place where all of these, let's say, industrialization efforts that you have in terms of the sensors and instrumentation will be impeded again, because you will need to create a new metric, you need to verify a new metric, and all these kind of things. So I would strongly advocate here actually to stick to particle number counting, at least for the ultrafine particles. And from what I heard also now about the submicron particles and the optical sensors there, it probably also makes sense to rather stick to counting metrics here.
Mm-hmm. I will agree a little bit with you, or not a little bit, I will agree with you, because of the fact we see the same thing happening with other pollutants out there, even gases. You will see that WHO is always using mass-based measurements or limits, and I think this is because of what our previous commenter said, right? Like, from a medical perspective, they always rely on mass. But instruments, they don't measure mass, even for gases, right? So they always have to measure them and convert them. And the problem is that during conversion, even I have seen that in real life with real instruments from different manufacturers out there, that even if they have sensors to measure temperature, atmospheric pressure, they don't use them to provide the conversion of the parts per million, parts per billion into mass values, which now creates a value that it's not accurate to what you have measured, in my opinion. So for this reason, at Go AQS, for most of the pollutants out there, gases specifically, we have parts per million, parts per billion.
I mean, but for gases, it's still accepted metric in a certain sense, I would say, yeah, because there's like a lot of let's say industries that measure gas concentrations in parts per million, parts per billion. Even let's say on the emission measurements, when you look at the automotive industry, they do that. So in that sense, there I would agree. But as I say, like all the ultrafine particles, I mean, you would really exclude some of the technologies, for example, low-cost CBCs there that cannot then derive the LDSA unless you put an additional instrumentation that makes, again, everything much more complicated, and you're kind of reducing the technology openness to actually create these low-cost sensors that you would need to actually roll this out at a large scale.
Yeah, and then again increase the price of the product, right?
Yeah.
Aaron?
Oh, sorry. 1.2, also when you're doing gas measurements, ppm and mass are easily convertible because you know the molecular mass of the product of what the constituent gas is. So they're synonymous because you know air is molecular mass, you know the concentration. In ppm, you can convert back and forth to mass. In particle mass, like the other speakers, like it's complicated. What is mass? You can have an EPA standard, you can have a BAM mass measurement, you can have a TO mass, you can have an optical mass. Who's mass, right? So it becomes confusing. Number count is a fundamental measurement. In theory, a fundamental measurement. Turns out it also has challenges too in this ultrafine range. But I think that kind of mirrors it. I think settling, and I think one thing we might want to be careful about is the letter M and N, because when spoken, they can sound very similar. Someone might say PM and say PN. We may want to think about not using the exact same nomenclature as PM and then saying PN, because I have a feeling that might be a problem later on, or we just need to be explicit and say particle number count parentheses PN. So in conversations, it doesn't come to it. Or
which is why I suggested, like before all this thing got popular, we always use sub P.
D sub P. Oh yeah, diameter part. Yeah.
And you can say D sub P1, D sub P 2.5, whatever. They're very clear that we are measuring a diameter and our technique is particle counting.
Yeah. No, I think that
That removes all confusion. We can directly communicate with the community. This is what we are doing.
Yeah. Or
least-
PNC as well.
The intent here is we want to create something that people will follow. Let's not add to more complications. Let's not be ashamed of what we want to do. Label it. This is what we're doing, folks. And here it is. When we get feedback, we'll revise it. If we don't get feedback, this is what we are proposing.
What about PNC? Do you think it gives us a
I
clear
would
message?
strongly recommend the P part of it completely. That just leads to confusion.
Yeah, I mean, I think, or you have to be very strategic with how you do it. But I think it'd be advantage to just use a term that's different, that isn't the two same letters with one dash missing.
So I'm saying the opposite. Yeah, call it D, and the sub we put it PM. You will not get rid of PM, but it's downgraded in its importance to what we are trying to do. We are measuring D, guys, the diameter.
Sure.
And we are saying, okay, it's PM below. So everything is derived, not measured.
Yeah. So
that keeps it clean.
Yeah, I think I would just take that as an action. And anytime you do a standard, the first thing that everyone argues about is terminology and naming, and no one ever agrees, which is okay because everyone has inputs. But I think settling on that might be really important early to get everyone aligned. And Lydia Morowaska is going to have very different opinions than all of us. So I think
did you know her opinion on that?
I just know Lydia has a lot of opinions, so, and a very specific direction that they want to go in all the time. So, and I love her. So it's not a criticism. It's just, everyone that's going to come from this. So finding consensus in the naming standard would be probably the first thing. But in general, I think you're establishing, at least, and I haven't heard anyone else in the group, but people should maybe just do it. You should just do a consensus roll, a question, and see, does everyone agree that we want to move to a PN, or I'm not going to use that myself, a total number count standard based on some size. Because then we get to argue about what does 0.3 mean? Is that 0.3 optical? Is that 0.3 mass? Is median diameter? Is that 0.3, whatever you want to, however we want to define what 0.3 is kind of the next argument. But I think if you establish consensus on a number count, that I think is really, one of the key things to reach.
That's my point. We don't need to apologize what measure we are doing. When we get into trouble, I will object. We try to equate it to something else we are not measuring. Like they say, we don't need to apologize for what we are not doing. We'll only state what we are doing.
Yeah.
That's when you get good standards, good documents.
All right. So I think it's very early at that point for us to recommend any limits, even for submicron or ultrafines. But at least what I wanted to do during this call is ask the researchers and the people that they are joining us, and potentially they are taking measurements in a variety of environments, to share their findings when it comes to ultrafines and submicron particles with us, in order to have a little bit better understanding of what's happening out there in different environments, and potentially, guiding folks out there with the right directions when it comes to what the number should be around those particle sizes. Right. And then another question that I have about ultrafines is that in many cases, I see that they say 100 to 23 nanometers in size particles for the total number, and in some other cases, 100 to 10 nanometers. Those are the two predominant, let's say, ranges. Is there any comments on that? Aaron, you're the first.
I don't think there's any definition of ultrafines. All we know is when you go to nano, it's generally accepted when at least one of the dimensions of the object is in the 100 or smaller nanometers, then it gets into the nanoscales. Ultrafine is anything bigger than that.
Yeah, most cases they will say anything less than 100 nanometer. But then if you dive deeper, you see that even the difference between particles between 10 and 23 microns, they say that you can find concentration of up to 300% more particles just between these small ranges of 10 and 23 nanometers.
That's always true. You smaller the particle, more the counts,
Mhm.
very little the mass. So we're not going to be able to set a standard or a method for measuring those. So let's not worry about it. It's all included in the submicron anyway.
Right, but I think it's saying to give some kind of a definition when we say what's the lowest number that you can
We
measure.
can define it, but we cannot measure it. I mean, even particle counters, contrary to what all the manufacturers might do, the physics, its most sensitive range is about 0.2 micron to about 3 or 4 microns. Less than 0.2, the efficiency drops dramatically, count efficiency. More than about 4 microns, the losses are so large, you don't get good data. So typically we don't use, in aerosol science, we don't use a particle counter much below 0.2 and much above 2 microns. Simply, we want repeatable data.
Okay. Aaron?
The physics, it's not the instrument quality. The scattering, light scattering is inefficient.
Yeah, I think how I would establish this is based on the metrology. So I would say the choice that you have, which is saying like P number count of particles greater than 0.3, is a good metric, and that is how kind of the clean rooms do it. They do it kind of number, and that is because you're going to pretty much say we're going to use low cost optical counters, right? Like that is going to be the future until there's another sensor technology. If you want to do indoor air quality, it's going to be low cost sensors, and they're going to be primarily optical counter. So establishing that, and why 0.3? Well, the light scattering intensity of a particle scales in that size range about dp to the 6th power. So actually, it's not entirely, it's about dp to the pi power. But either way, to go from 0.3 to 0.25 is incredibly difficult from an optical standpoint. You have 0.1 micron particle counters, optical particle counters. They use Heine lasers because you need so much intensity. So establishing your standard as being just count bigger than this could be sufficient in saying, look, I'm just going to capture everything that's larger than this because I know they're good counters. They're not good sizers, so we want to be careful about putting size bins. And what does size tell us? Not really anything, actually. It turns out, like, we know in the optical range. When we go to the other side, a little bit more information there. So establishing a metrology around 0.3 is fine, and saying I'm just going to count everything bigger than 0.3. And you may even want to say 0.3, and you're going to define some optical characteristics that define it as 0.3. When we go to ultrafine, it's a whole nother game. I do slightly disagree. They make condensation particle counters that go to single-digit nanometers now, right? Like the Finnish group, I'm blanking on the Finnish group's name, so I'm so sorry to them, but like Juan de la Mora, all of these people are playing in what is the difference between a gas and a couple molecules put together and an aerosol, right? We're in this, like, what is this space? But I think it comes to a different portion of discussion. And this has happened before already with the Euro 5 standard, right? When they introduced the number count standard for diesel engine emissions, it becomes, what are you trying to measure consistently? And the reason that you use 23 nanometer cut points with diesel engine emissions is because you have this nucleation mode, these tiny little volatile particles that do not hang around forever. And if you measured them, depending on how you structured your exhaust instrumentation, you could get them or you could not get them. And so the idea was, let's ignore these things that are not consistent and volatile particles, and we're going to get some solid number count from 23 and larger. But you can make a CPC go to a single. You can make a diffusion chargers go probably as low as that too. I think it's all doable. But you want to start to think about that threshold as being driven by the mechanism of the formation of particles. Do we care about nucleation mode particles that exist in the atmosphere outdoors that don't penetrate homes? Because I think one piece of information is, look at the penetration of ultrafine particles in there. There was a recent paper by Brent Stevens who looked at Chicago-based homes. So I'm preference because I live in the Midwest too, so I was very interested in it, right? Not surprisingly, the ultrafine penetration into the building environment is in those particles between 0.1 and 0.3, right? The hard to filter particles because they have limited diffusion, limited mass. The really, really small stuff didn't really penetrate the building environment because they got filtered through the building envelope as they made it into the space. So when we start thinking about indoor standards, we think about what are the sources of generation, how long do they last, and then how do they affect the body, and how do we come up with it? Adding size to me becomes very complex and can be done. Diffusion chargers can do estimates of size. You can make a mini SMPS, but they're kind of expensive. Like there's metrology can do, but it's never going to be cheap. And if we're thinking like the next generation of ultrafine, it is the delineation is the generation mechanism, do you skip the nucleation mode and do something like 10 nanometers? So you're kind of ignoring most of these temporally volatile particles and looking at what hangs around. Again, there's a health study that comes to all of this. What's the health effect of particles between 1 and 10 nanometers? Nobody knows. I think because it all gets lumped together, right?
Yeah. So
the question is, do you hit on consistent, repeatable metrology, or do you try to get something? And I think that my answer is, and this is what, Wiedenholler has been arguing about outdoors forever. That's kind of why they picked 10 nanometers, right? You're just away from the nucleation mode, that your number count is heavily influenced by temporarily spontaneous creation of particles, and you're really looking at the stuff that hangs around for a while and is forming the larger particles that grow to 0.3. So that's kind of how I think structure it, based on the 0.3 is optical and just committing to some metrology-based techniques, and the other side is talking about what are we measuring and what are we measuring consistently. I don't really have a skin in either way of the game. You can make a particle on a CPC go to a single nanometer, but like, what are we learning and how expensive is it and what does it tell us? And I think the answer is,
for me, if you were interested, what we are trying to do would be most useful. It has to be simple.
Yeah. And
it needs to use readily available gear. And we can put all the other arguments or discussions in a preface or introduction, why we are doing it. And then tell them, this is what we're doing, guys. This is the instrument, good, bad, or ugly. We're going to pick this grade of instruments, which anybody can buy. And this is how we are proposing the limits are. And here are the reasons why. Will we change our mind in 5 years? Probably. But right now, this is it. The simpler it is, the easier it is to promote it, easier for people to accept it, quicker we'll get the feedback. Oh, you guys are full of it. Completely wrong. Then we can go back and ask them, what is wrong? How do we fix it?
Right.
That's how I'd approach something completely new like this. Otherwise, we're going in the same path everybody else has been trying to do. They're still talking.
Yeah, and to throw it to, I was going to say, Florian, you should jump in.
I got to run, guys. I got another meeting. Thanks for inviting me.
Thank you.
Soon.
Thank you.
Thank you.
I just wanna comment. So I think 23 nanometer, Aaron was completely right. At some point, it was decided to do that because of reproducibility issues in, let's say, the automotive industry. But I think now the move in all the industries has already gone to 10 nanometers. So I think that's something we should not even consider anymore. I think 10 nanometer is not right now something that has been established as a lower limit, let's say, for a lot of metrics, whether it's the automotive emission side, whether it's the ambient monitoring with Wiedenholler and the AQS network, what they define as a lower cutoff. So I think the lower cutoff for ultrafine, for me, is more or less already fixed in the scientific community if you really want to talk about the standard. Of course, there's, let's say, scientific, measurements that go below that to single-digit numbers and see how, 3D printer particles evolve over time and things like that. There's things like that out there, but I think for a standard that's just not feasible at the moment. What I would actually comment more about is actually the upper limit, because you're saying like particle number count from 100 nanometer to 10 nanometer. I don't think we should define an upper limit, at least not such a low upper limit for ultrafine particles. Because the reason is, first of all, you often have these coarse modes. For example, a diesel mode, it's centered around 80 nanometers, but extends quite far, even above 100 nanometers. It can be quite coarse. So you have a lot of particles that are also larger than 100 nanometers, and we are not even aware of all the other sources that are out there. So if we cut off the limit at 100 nanometer there, we actually have a blind spot also with our other submicron standard, which then starts from 0.3 micron, which to me doesn't make sense. So I would say there's some people that define ultrafine particles as particles smaller than 100 nanometer, but I think it's more like a, let's say, scientific, or distinguish them from the micron-sized particles to say, like, this is smaller than 100 nanometers, there's particles smaller than 100 nanometers, but the modes are usually also extending 100 nanometer. So I would, then there's actually one thing I want to comment about the concentration that you experience. Just an example that I experienced at some point in the automotive industry. I remember we had a standard where we had to do a check where we sample ambient air with our instrument, and it needed to go above 100 particles per cubic centimeter. And then all these test cells in the automotive, they got new ventilation systems with new filter. And apparently we could not reach the 100 particles per cubic centimeter anymore in that environment. So if you have a good filtration system and a good ventilation system, you can even get below 100 particles per cubic centimeter, at least in an industrial environment. That's absolutely feasible. Whether this is something that you want to propose for indoor, let's say, standards, that's a different story, because you have indoor sources that will for sure affect your concentration.
I don't know. We have only 3 minutes left.
It's
you're the
intense.
boss. You cannot go to me, you can skip me, or you can go to me. You're the boss.
No, you're the next one, so you can.
All right. I think I mirror Florian's statement, which is, I think if you do your standard just particles bigger than this, so if you say UFP is, and Florian said 10 nanometers, I think we could argue a little bit about that, but 10 nanometers and larger, and then it's 0.3 and larger. If you want to know the difference between 10 and 0.3, and you co-locate an optical counter and a CPC, you can start to infer what is between 0.1 and 0.3, right? And so if you spill the standards, just things bigger than this, if people want to infer, they can, but it's easy to just say, because a CPC is going to count bigger too. You can't size select and have a CPC stop counting at 0.3. So if you view it from the metrology standpoint, it makes it easier just to say total number count greater than 10 nanometer, total number count greater than 0.3, and start to establish the criteria there. The reason that I think the cutoff is, and I think we should be careful about mirroring what Europe is doing. Again, no harm and no shame in doing 10 nanometer cut. The origin of that came from the CPCs they were using, 3010s. They had a 10 nanometer cut. If you look at other CPCs like Suzanne Herring's water CPC, it has a lower cut point and it's cheap. So then it's kind of a question of like, do you want really precise cut point for expensive instrument, or are you willing to sneak down to 8 nanometers or 7 for a cheaper device? And I don't know exactly diffusion chargers, what their cutoff cards. I don't pretend to understand it enough, so Florian can speak to that. But thinking about that from a cost standpoint and what the ROI is, and creating very specific cut points could be challenging. And I think it's part of the ASTM conversation that's happening here in other places. But I think that's all I got. But I didn't mean to start arguing for you. I'm sorry. I'm very sorry.
That's fine when it comes to bigger particles, even 300 nanometer, because the number that they are going to add up is relatively small, right? Yeah. But if you go smaller than 10 nanometers, I will assume that the number may go even higher. So now when we are trying to compare different environments, indoor environments, if you like, from different places, in order to set some kind of range of safety, then it becomes challenging if you don't have those numbers in place in order to...
I think you're going to have a challenge either way, because there's no defined standard. So like you're just picking a number, but it's okay. I understand.
But you know that we are also trying to invite the scientific community to investigate more with that. We are not going to establish a range of safety today at Go AQS here, but we would like to do that, like invite scientific community out there, start measuring those particles in different environments in order for us to get an understanding of what's happening and share this kind of information with epidemiologists that eventually will create, the safe levels of exposure for those particles. Florian, we are out of time, but...
Responsible for the diffusion charges, I can say that the lower it gets, the more difficult it's going to get for diffusion charges, that's for sure. So like when it goes way below 10 nanometers, it's going to be difficult. And then you have also the problem about the calibration in the end. So you have all these calibration facilities in terms of reference setups that are now moving towards 10 nanometer and calibrating a CPC again 7 nanometers. If you go below, it's always getting more complicated. So it's not only about the cost of the device itself, it's also about that you can actually make them reproducible. Of course, we will not, for low-cost device, we will not have a traceable ISO 17025 calibration, but at least we would need to agree on a way of how to calibrate and how to verify that the cutoff is actually where it should be. And that's again another very complicated topic if you move that further below 10 nanometer, because for 10 nanometer there's like just a lot of standards that have been established already that are working.
All right. I think it was fantastic this afternoon meeting, actually, because we had the chance to have two people from two different metrology systems, one CPC and another one with a diffusion technology, ultrafine measurement system, that gave us a little bit more perspective on what the technology can do for us, right, on that specific area. And during the morning, we also had people from actually that they advocate for the lung deposit perspective because they do research around that specific area. So they were more, if you like, interested in seeing those numbers in reality and setting limits around those numbers because it's their work. But it is very important to have those different voices and understand what one is proposing, what the other is proposing, what's the reality at the end of the day, in order to advance in this specific field, right? Which is, at the end of the day, what we are after in here. All right, I would like to thank you all for joining this session today. I will try again to summarize everything from both calls today and provide an article with all of you in order to comment or provide additional information with us. But remember, we want you to provide us with measurements in different areas and different places of ultrafine and submicron particles in order for our minds to start understanding better the reality of those particle sizes and what we can do about them in order to reduce our exposure to them. So thank you once more. I wish you a great night, morning, wherever you are, and see you next time.
Yeah. Thank you.
Bye.
Dos cosas, creo.
Bye.
Vale.